Assalamu alaikum. Welcome to the 11th lecture of natural language processing. Today, we will start discussing logistic regression, the other probabilistic model. Previously, we discussed naive-Bayes classifier. So today, we'll talk about logistic regression. And so that's kind of the main topic for today. Previously, we had discussed naive-Bayes classifier, specifically the multinomial naive-Bayes classifier. And then we discussed the evaluation of classifiers in general. And I might start with just repeating some key concepts from the evaluation of classifiers. And then we will move on to logistic regression. So the whole idea of discussing classifiers was in the context of text classification. So as we said earlier, text classification have many applications, from topic classification to spam filtering to, for example, sentiment analysis and so on. So you can think of any and many applications that can use text classification. And the typical approach is to have a supervised machine learning approach, where when you are given a training data which has labels, the learning model learns that model or behavior from text to label, and subsequently you can apply that model on new data set, and that model will give you the label for that particular document. So so today we also have a quiz at 11:05. This would be your fourth quiz, and most likely this would be the last quiz before your mid, which is scheduled next weekend. And we will have a class on Tuesday, and perhaps on Thursday we might have a review class. Just all up to you. So we will let you know what decision we make. So any questions before I get started with the content for today? So let me just quickly review the process of evaluation. The whole idea of evaluation is that we want it to be a true representative of the performance over the population. And the usual approach is you have what is known as a train test splits. So you have some data set which is labeled, you split it into two. The training set is used to learn the parameters of the model, and the test set is used to evaluate or estimate the true performance of the model. And if your model has hyperparameters, then we split it into three ways. So we have train, validation, and then the test. So validation set is basically then used for tuning the hyperparameters of the model. Of course, in naive Bayes, we don't have any hyperparameters, but some other approaches like neural networks would have hyperparameters. And of course, you report your performance on the test set after you have trained it over the training validation pair. So this is the simplest, you can say, reliable way of estimating the performance of a model. So there are many other approaches. So you can use cross-validation. So in cross-validation, you basically, in general, we have k-fold cross-validation. So k usually would be 5 or 10, for example, for most practical applications. So what that means is you run the model 5 times, or you train the model 5 times, and you test the model 5 times. And in doing so, you test over the entire data set. So let's say if k is equal to 10, you will get 10 performance values. So there are two ways of reporting these values. You can either report mean plus minus STD, or basically you report the performance over the entire data. So when you do cross validation, you will have results over the entire data. So that would be just one value. So let's say accuracy over the entire data. So you will collect the values from all those 10 folds and report it as one value rather than separate values and taking the mean or standard deviation. So that's cross validation. And to get better estimates or more robust estimates, and then hopefully also build confidence intervals, we will usually use resampling techniques. So resampling basically means that you do it multiple times. Of course, in cross-validation, you also do multiple times. So that in a way is a resampling technique. But resampling is often more closely associated or linked with multiple samples of trained test. So randomly, you extract a training sample and the remaining becomes a test, build a model, test a test set, and you can do this multiple times. In fact, you can do this 5, 10, 15, 100, and so many times. It can be done as many times as you like. But of course, for each time, you'll have to train the model or learn the parameter. And then, as before, you can report mean, minus, and standard deviation. And depending on distributions, usually we assume a normal distribution, you can also report confidence intervals. So confidence intervals essentially means this. I won't go into the math of that because that would be too much statistics in a course that is primarily NLP. So confidence intervals can be one-way confidence interval. So CI, for example, so one way basically means that, so you can say accuracy is greater than equal to, let's say, 80% with some confidence, with 95% confidence. So that would be one way. The two-way would be, so accuracy is between, let's say, 75 and 85 with, let's say, 95% confidence. So two-way would give you the upper and lower bound, and one way would tell you how likely, with some confidence, of course, the accuracy lies above some threshold. And in NLP, we also sometimes use another approach, and that is more appropriate when you're comparing classifiers. Of course, you can use the previous approaches to compare classifiers as well. So let's say you have a classifier A and you have classifier B. You apply cross-validation and get the mean and standard deviation for A and get the mean and standard deviation for B. So, and then based on those values, you can make a decision whether A is better than B or B is better than A. You can simply compare means, or you can even do more elaborate pairwise, you can say statistical test. Of course, that would depend on the pairwise distribution and get some confidence intervals for two classifiers, the performance of two classifiers. So, but as I said, in NLP, another approach is sometimes also used, which is called bootstrapping. Why this is popular? This is more popular because training a model is very costly, especially nowadays when we have lots of data and we are typically training neural networks. So neural networks, we haven't started talking about neural networks so far, but neural networks are lots of parameters and their training can take a lot of time. So like, for example, in cross validation, you had to train the model 10 times. So training the model is costly. So bootstrapping essentially resamples the test set only. So you just have one trained model. So let's say you have a test set. So you basically do standard or simple random sampling with replacement, uh, and of the same size as the test set. And you do this hundreds of times. So let's say the test set size is, let's say, n. So your sample size would also be n. But of course, it is sampled with replacement. So there is a chance that some samples might be taken more than once, and some might be dropped out or not taken in any particular sample. But you do this like hundreds of samples. So take hundreds of samples and then compute performance on each of them. So now you will have performance values for, you don't need to train again, same trained model, but you run it on tons of samples, and those are obtained with, with replacement and of the same size as the test set. And then once you have those performance values, uh, you can report those values and compare them. Let's say if you have two classifiers, you can report their performances. So those would be more robust comparisons. And if you want to do even more robust, you can apply some statistical test. So and again, there are various statistical hypothesis testing approaches available. In general, they can be parametric and non-parametric. So parametric, of course, as the name suggests, have some explicit parameters that you will need to take care of, usually in terms of the distribution that you're assuming. So you have a parametric uh, distribution for the samples, and non-parametric do not assume a fixed distribution for do not assume a model distribution for the samples. So, in the slides, I think I shared these slides. I have shared these slides on LMS. So I mentioned some popular hypothesis testing techniques here under both parametric and non-parametric. Of course, the details of each is somewhat beyond the scope of this course, but you will find implementations of these uh, in most tools. So as I said, also bootstrapping is a way of non-parametric uh, sampling, and typically non-parametric approaches, statistical test approaches are used in machine learning as well as in NLP. In the older days, parametric were more popular, but nowadays non-parametric are more popular. So in the non-parametric, you have uh, tests like signed test and the Friedman test and the Wilcoxon test and so on. So you can look these up and get a better idea of how these are applied in practice. All right. So any questions? Okay. Uh, so I had also mentioned or discussed some measures last time. So for binary classifier, you can have a lot of performance measures. For multi-class classifiers, you can also have some classifiers. And we also talked about macro averaging and micro averaging, which is more appropriate for multi-class classification. And so we discussed that last time. So let's now move on to logistic regression. So logistic regression is a classifier. But of course, you see the name regression there. You will get it become clear why it's called regression, but it's actually a classifier. So it's first of all a probabilistic classifier. Just like naive Bayes was probabilistic, this is also probabilistic. But in terms of the type, it is generally called discriminative. And I will mention why this is discriminative. Naive Bayes was generative. So it's a probabilistic discriminative classifier. And of course, you can also call this as parametric, but naive Bayes can also be called parametric. But usually this classification is not applied to naive Bayes and uh, logistic regression. But you can make the distinction because you have a linear model at the end of the day. Anyway, okay. So what is logistic regression? Remember, we applied the Bayes rule C given X. X is, of course, the representation for the document. So if you apply the Bayes rule, you get probability of X given C, probability of C divided by probability of X. So this is the Bayes rule applied. So the left-hand side is often called a posterior probability because it gives you the probability of the class given the document or given the representation of the document. And the right-hand side has several components. And we said that in naive Bayes, we estimated this side, these parameters or these probabilities. We estimated these probabilities. And from these probabilities, you can actually regenerate the data. So that's why this was called generative models. Why? How can we regenerate the data? So you can generate a class according to the distribution probability PC. And so you can generate a class C according to PC. Let's say this is a distribution PC. You generate a class, and given this class, whatever that is, 1 or 2 or 3, remember, if it is K class problem, you then generate a sample or X given that C. And that sample X, of course, is an example of a document belonging to that particular class. And you can repeat this process randomly according to these distributions to regenerate the data. That's why it was called generative. In logistic regression, on the other hand, we are estimating this posterior probability directly as some function of, in general, X, your representation, and C, the class. So some function. So this is a parametric function. So F, X, and C. And this, of course, is the general idea for discriminative classifiers. You get the posterior probability directly from a function, F. So in the case of logistic regression, this function is the logistic function. And that function actually has a basis also. Maybe I will mention that as well. But let me okay. So for the logistic regression, we have F as a logistic function. And okay, let me just write it like this. And within that, you have a linear model. So I will write this in terms of vectors now, T, X. So in general, vectors would be bold. And the T is for the transpose. Vector, whenever we write vector in the purest sense, it should be a column vector. Vector is always column. So that's why W ke saath transpose laga, it becomes a row. Row multiplied with column to give you a single value. That single value then is fed to this function, and that function outputs a single value. So on the left-hand side, what do we have? It's a probability. So this single value must lie between 0 and 1. Okay? So this single value must lie between 0 and 1. Otherwise, it will not be a probability. Okay? So this kind of dictates what f can be. So f, the function f should always output a value that is bounded on the upper side by 1 and on the lower side by 0. And one such function that satisfies this is the logistic function, or sometimes also called the logistic sigmoid function. So this is like an S function, and the function is 1 divided by 1 plus exp, which is exponent minus the input to the function, which in this case was okay. Of course, so far I'm writing this in terms of binary classification, and we will shortly discuss how we got to this function. So in essence, probability of C given X is now given by this. So if you are able to estimate the parameter W on the right-hand side from the data, the training data, you will have this functional form of the posterior probability. Now, given any new X, you have the W's, you put the W's in, this function would give you the probability of C. Okay? Which is the probability for class, one of the classes. So far, this is built in terms of the binary classification. So let's see how we got to this. Okay, this is one way of looking at logistic regression, functional form of the probability. But actually, for this particular case, for binary classification as well as for multi-class classification, you can actually derive this functional form directly from Bayes' rule. So let's quickly look into that. So what did we have as the posterior probability? So we have probability of X given C, probability of C divided by probability of X. Okay, so this is the Bayes rule. And let's say we are talking about so let's say we are talking about classification with C is equal to 0 or 1. All right. So two possible values for C, C0 and C1. Okay. So let's say I've written this for what's happening here? Okay, right brace आ गया इधर. ठीक है, यहाँ ये आना था. वर्टिकल बार, ठीक है। कॉपीराइट भी आ रहा है। ये मुझे ऑफ करना पड़ेगा, ऑटो करेक्टर। ऑलराइट, तो प्रोबेबिलिटी ऑफ c इज इक्वल टू 1 इज गिवन एज सच, ठीक है। ऑफ कोर्स राइट हैंड साइड में भी c इज इक्वल टू 1 होगा, मैंने नहीं लिखा हुआ। सो इफ आई टेक द राइट हैंड साइड and or let's look at the denominator. Okay, let me write it again. Probability of x c, probability of c divided by probability of x, we can write it as a summing out probability of, and of course in the conditional form, x given c equal let's say 1, probability of c equal 1 plus probability of x given c equal to 0, probability of c equal to 0. So you can also write the denominator in this way. This is actually summing out or normalizing the probability. And of course, we are summing out in the conditional so that we get the same expression as the numerator. So if you divide with the numerator, both the numerator and denominator, what do you get? You get 1 up there. And in the denominator, you also get 1 plus you have probability of x given c is equal to 0, probability of c equal to 0, okay, and then divided by probability of x, c is equal to 1, probability of c is equal to 1, okay. Are you following me? Dividing both the numerator and denominator by probability of x given c is equal to 1 and probability c is equal to 1, right? So you notice that we are going closer to the logistic sigmoid function. ठीक है? So again, taking the right hand side, ऊपर तो 1 आ गया, denominator को देखते हैं सिर्फ. So denominator, तो denominator में मेरे पास 1 plus, ठीक है? So I would use a, you can say, what can you say? Equivalence, you can say relationship exp and then natural log. It will give you the same thing. Both of this would cancel out to give you the same thing. So you get x is equal to c equals 0, probability of c equals 0 divided by probability of x c equal 1, probability of c equal 1. ठीक है? So one more step and then we are done. So exp, which is exponent, and natural log. I put a negative there and reverse the order of the fraction. This becomes 1. and denominator becomes 0. So you now have the very similar function to logistic regression. 1 divided by 1 plus exp minus something, let's say a. So that a is that expression in log, natural log. And that expression is called the log odds for uh, the Bayes model. And you can express that in a linear function. So what we are essentially doing now is a is basically ln probability of x given c is equal to 1, probability of c is equal to 1 divided by probability of x, c is equal to 0, probability of c is equal to 0. So this is our a, and this thing we are writing in terms of x as a linear model. What is W transpose X? Essentially is W naught X naught plus W1 X1 plus W2 X2 plus, of course. So these X's could be your words in your text document, or in general, X would be any feature. And the corresponding W are the weights or parameter for that particular X. Okay. So we are representing the log odds as a linear model, as a linear function. And the overall function that we get is a logistic sigmoid function, which would always output a value between 1 and 0, which of course can be interpreted as probability. So this function always outputs a value which is continuous between 0 and 1. So you can think of y is equal to probability of c given x as the sigmoid of W transpose X. Okay? So the output of this function is actually continuous. So that's why this is called regression. But that output is a probability, and the probability for class 1. And we don't really use it for regression problems, we use it for classification problems. Okay, any questions? So this was somewhat involved, but relatively simple use of probability theory and Bayes rule. Just to show you how logistic regression formulation is developed for binary classifiers. For multi-class classifiers, you can do the same thing. You get a slightly different function. I'll write that later, but I won't derive that. Just so let me show you. Uh, let me see, just hold on. Okay, so if I draw the sigmoid function, So it's just like an S function. Of course, from 0 to 1, and it has, so let me go to the next slide. So basically, the x-axis 0 is here. So it's something like this. So from 0 to 1, and at, of course, this is a here. X-axis is a, y-axis is, of course, the function value. So function value has a value of half when a is equal to 0. Okay? So when a is equal to 0. So what was a in the derivation that we did? A was the log of the log odds. And what was odd? Probability of c x given c1 divided by probability of x given c0. So if, and of course that is also the posterior probability. So if both of them are equal, then you get 1. Natural log of 1 is 0. So it means that when both probabilities are equal, posterior probability is equal, you get a value of 0, which will give you a function output of half, 0.5. So you don't know which class it belongs to. But if a is on the positive side, a is greater than 0, then you will get a value that is closer to 1. If a is negative, you get a value that is closer to 0, which means that it belongs to class 0, otherwise class 1. All right, so let's move on. So these axes, as I said, can be the same as words. Any features that you find appropriate for your text classification problem, usually they are words, but they could in general be anything else. They could be multi-word combinations as well. They could be any other thing, let's say the presence of some particular punctuation or some particular date, or it could be even be some other thing that you're adding to your text classification problem. Maybe it's a picture information that you're adding to the text classification problem. So in this parametric form, or in this sense, logistic regression is somewhat more powerful than naive Bayes, because you can represent or you can take those features to be anything that is appropriate for your classification problem. Okay, so now we have this function here that I've written. This is essentially the model for the binary logistic regression model classifier. Okay. The output is y, which is an estimate for the posterior probability of c is equal to 1, given the document which is represented as x, the feature set x. Okay. Now the second question is, how do you ensure that, of course, y is the estimated value, which of course would also lie in 0 and 1. Remember, it's a probability. And c was actually just two possible values, 0 and 1, right? The actual true value, which was in the data set, was either 0 or 1, but our output value that we are getting from our model that is learned from the data is a continuous value from 0 to 1. Ideally, for a model, for a data that for a problem with label 0, y should also be 0. And for a document with label 1, y should also be 1. But of course, they would in general not exactly be 1. We would like them to be closer to 1. So how do you ensure that happens? We have to formulate a optimization problem and define an objective function. So that is called an objective function. or loss function in the context of machine learning. You typically call it a loss function. You can also call it a cost function. So for the binary classification problem, the most common popular loss function is what is known as the cross entropy. And entropy basically quantifies the homogeneity or inhomogeneity between two variables. Okay? We call it cross entropy because there are actually two variables here. Uh, in general, entropy is the homogeneity of, let's say, a particular one variable. So this is cross entropy. We are tracking the homogeneity between two variables. And what are those two variables? Y and C. Y is our estimate. C is the true value. So what would we like to desire? We like Y to be as homogeneous as possible with C for all the training examples. So what would homogeneity imply? It would imply that entropy is close to zero. Okay? And we would like to thus, so our basically loss function, we can call L, which is a function of the parameter W, is basically the cross entropy between uh, C and Y over training data. Okay? So if I want to write it in terms of equations, so we have basically this expression. So you will have to sum over all the data points. Okay? So let me say I, and then we define the entropy minus so so I'm going to use I as the index for the examples. So in the training set, which would range from 1 to n. So, and I use it as subscript y I into natural log of probability, or simply Ci per minus. Entropy is, of course, what? The variable multiplied by the variable itself. Say this is cross entropy, the two variables here are y and c. And the other one is basically 1 minus y. I will mention why this is this way. Ln 1 minus Ci. So this is cross entropy. So remember, y ranged between 0 and 1, and C was either 0 and 1. So there are only two possible values. So let's say if a particular example, let's say example 3, I is equal to 3, let's say, I is equal to 3, C is equal to 1, meaning that it's a positive class. If C is equal to 1, then the second expression, which is 1 minus C, would become 0. And I think I wrote it. I think I wrote it right, or just a second. Second expression will become 0, and the first one will be 1. Okay, yeah, that's right. Okay. So if C is equal to 1, okay, if C is equal to 1, the first expression, probability of C, would become natural log of 1 would be 0. So first expression goes away. Okay? And we only have the second expression, which is thus computing the or estimating uh, the entropy between C and Y. On the flip side, if so, you have only one expression at a time that is used in the summation. So if the class was 1, then the second expression is used. If class was 0, then the second expression would be used. If the class was 0, the second expression 1 minus 0 would give you a value of 1. The second expression becomes 0. Okay? So this basically sums the entropy, or specifically the cross entropy, over the entire data set. And of course, this becomes a minimization problem. We would like to minimize this. Why? Because we want to reduce the entropy, the homogeneity, the inhomogeneity between C and Y. So minimize LW. So this is our optimization problem that we would like to solve. It's an unconstrained optimization problem because there are no constraints. And in general, for most machine learning problems, this is a convex optimization problem. So what does convex optimization means? If you use any first order or second order optimization technique, you will reach a minimum which is the global minimum. So you will be able to find the global minimum using those techniques. Okay. 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 So is this clear? So we have the model, which is a parametric model. Y is equal to sigmoid of W transpose X. W transpose X is a linear in X, as well as the parameters, of course, multiply with each of those X. So that is the model. We want to find the parameters. We have a training data set. We minimize the cross entropy between the output that is estimated Y and the true value, which is C. And the cross entropy का formula यहाँ मैंने लिखा हुआ है. So it's an optimization problem. As I said, this is going to be convex optimization. The minimum that you find would be the global minimum. And at that point, the value that you get, so if you solve it, you will get W star, the final parameters, or I would say optimal parameters. And now once you have those optimal parameters, you now have the model. So you can use this model to make new classification. Given any new document X, you have all those Ws, put the values into this function. This function will give you the probability of class 1. Y is the probability of class 1. So if this probability, for example, is greater than 0.5, you say that it belongs to class 1, otherwise it belongs to class 0. All right. So any questions? So it's somewhat important to discuss logistic regression because this is the basic building block for neural networks and deep learning. So a deep learning model is essentially multiple logistic regression models in series, as we will see next, I think in the couple of lectures. Okay. So logistic regression essentially is the building block for neural networks. Okay. So we have talked about the model, the loss function, and the optimization of that model, that loss function will yield the optimal parameters. So how do you minimize or optimize this? There can be various algorithms that you can use. Uh, you can also, as I said, you can use second order uh, optimization techniques as well. For example, Newton's method can be used, but more commonly, and which is more appropriate for neural networks, we typically use first order stochastic gradient descent. Or simply the gradient descent approach. So this is an iterative optimization technique that gradually uh, moves along the cost surface until it reaches a minima. So since in this particular case there's only one minimum, so that minimum is also the global minimum. So usually, of course, in the neural network context, we usually be using the stochastic gradient descent. But if you look at logistic regression implementation in most toolkits, they will use Newton's method. And उसको थोड़ा सा उन्होंने tweak किया होता है in terms of gradient descent or the least square problem, और उस particular technique को फिर वो कहता है iterative reweighted least squares. So ये detail typically we cover in a machine learning course, so I'm not going to discuss it here. So iterative reweighted okay. So the Newton, so this basically use the Newton method for optimization in an iterative way, of course. Okay. All right. So now, so we have about 10 minutes. So let me quickly discuss the multi-class logistic regression. So previously we had discussed and even formulated the binary logistic regression model. So multi-class where k is greater than or equal to 2, or in general greater than 2. So you will need to have models for, you need to have k models. So previously we had just one model and we found the probability of c is equal to 1 given x. And we knew that the probability of c is equal to 0 given x would simply be 1 minus p is equal to c is equal to 1 given x. Okay? But if you have multi-classes, you will have to find the probabilities for all. So probability of c is equal to 1 given x. So probability of c is equal to 2 given x, and so on. Okay? So all of these would need to be estimated. So for in the case of multi-class logistic regression, we have a separate model for each of those probabilities. Okay? And that separate model is, let's say, y. Let me denote it by the superscript k, not the power, but the superscript k is basically what is known as the softmax function. Softmax function of w. I'm using the power to denote this parameter is for the kth model and transpose x. Okay? So of course for k is equal to 1, 2, 3 up to k. So there will be k models and k set of parameters wk. Okay? So what is this softmax function? The softmax is also called the normalized exponent function. So essentially, if I write this function, this is exp w k, the kth function up there, and in the denominator we have the sum of all those exponents. That's why this is called normalized exponent. So sum for all k from 1, 2, 3, 4 to capital K of exp. Let me write it. K दे देते हैं, K notation सही नहीं, J कर देते हैं इसको. So so exp w j, so the sum of all those exponents. So that's why I said it's called normalized exponent. ऊपर एक exponent है for the kth parameter for the kth model, and नीचे सारे exponents का sum है. ठीक है. So this is the softmax function. And again, this value would range between 0 and 1. This is a property of this function. And of course, as you can see, normalize ho raha hai, obviously it will not go more than 1. And exponent is for a positive as well as a negative value would always be a positive value, non-negative value. So 0 to 1 के दरमियान ये range करता है. ठीक है. So this is the model for multi-class classification in logistic regression. In other words, you have k separate models, and for each of those k, each model we have a separate set of parameter w. Okay. So if you have a k class problem, and you will need k set of parameters. और इसमें जो loss function है वो भी similar है, but it's usually called a multi-class cross entropy. ठीक है. So I would not write the formula for it. It's kind of messy, but this is the very similar to that. Of course, there are multiple classes and multiple variables, so that's why it becomes messy. But it's similar to the binary cross entropy. So again, this is optimization problem. After minimizing or optimizing the problem, you get the parameters W star for each K. Okay? For each K. So once you have all these parameters available with you, given a new document with its X, you will compute Y1, Y2, Y3, and Y capital K. Okay? So these are the posterior probabilities for the document belonging to each of these classes, Y1, C1, C2, C3, and CK. और जिसकी सबसे ज़्यादा value होगी, that is the most likely or most probable class for this document. ठीक है? So this was the multi-class logistic regression. Previously, we discussed the binary logistic regression. We have also talked about the loss function and the parameters that you will learn after minimizing the loss function over the training data. And once you're done with that, you have a model that you can use to make future classifications. So I think that's pretty much all for logistic regression. In the next lecture, we will discuss mm, there are actually two options. I'm not too sure. Maybe I can talk about sentiment classification, or maybe I move on to straight to neural networks. Uh, Let me see what I will do next. ठीक है. So I think we have a quiz, so I'll stop here. So any questions? Sure. Any questions? So get ready for the quiz then.